Hi students, today we are going to see the most important topic of the lesson, the last topic, that is Gauss's law or Gauss's theorem, both are same, okay. This is also to calculate the flux. We already saw in other video how to calculate the flux, right? Phi is equal to E dot delta S, the same thing. Here also we can, this scientist gave the clear explanation about the flux. So first we want to know what is the statement, okay, important statement, because there are so many questions start like state Gauss's theorem or state Gauss's law, then prove it, some cases, other cases apply Gauss's theorem to calculate the flux due to three applications are there. First if we see the definition, let me read for you. The total electric flux over a closed surface in vacuum is 1 by epsilon 0 times the total charge Q contains or enclosed within the surface, you can say. Okay, that what is this one? The total electric flux over a closed surface in vacuum is 1 by epsilon 0 times the total charge Q contained in this surface. It can be capital letter Q or small letter q, no problem. Flux phi is equal to closed surface integral E dot ds. I explained you before what is that circle on the integration symbol, yeah. So is equal to 1 by epsilon 0 times Q. Remember this equation as well as the definition, okay, clear, yeah. Phi is equal to 1 by epsilon 0 times the charge enclosed, small letter q or capital letter Q, you can. Now proof of Gauss's law. Wherever you see the word Gauss's law, read it Gauss's law or Gauss's theorem, both are same, 100% same. Now this is a proof, usually carries 2 mark, okay. Sometimes state and prove Gauss's theorem 2 mark. Sometimes state Gauss's law 1 mark, then application question. So you write exactly as it is when there is a theorem statement coming. Now proof of Gauss's law. Suppose an isolated positive point charge Q is situated at the center O of a sphere of radius capital letter, we can write R, okay. So what I wrote here, suppose an isolated positive point charge Q is situated at the center O of the sphere of radius capital letter R, I like to present, small letter are also fine, there is no problem in that one, okay. Now draw one circle, completed now. Find the center of the circle and what we wrote in the statement, a charge Q is placed, right. So label it, plus Q is there at the center of the sphere. Now this is the time to mark the radius of the sphere. So radius of the sphere, mark it small letter R or capital letter R. What you are using, use that symbol in the derivation, no other importance for this variable. You know that there will be electric field going out of the positive charge, right? Because of positive charge, direction of the electric field will be away from the charge. So I marked outside the sphere, capital letter E. And area vector, remember area vector to any point is normal to that surface. Area vector of the top of this mic is normal to that one. Area vector of side of this mic is normal to that one. Okay. So area vector for a sphere is normal to the surface of the sphere. So now you can look into the diagram and understand ds, area vector, is parallel with the electric field. That is the reason I mentioned there theta is equal to 0. Okay. Got that point? That point important actually. Many places we are using. Angle between E and ds or E and delta S, area element, important. Most of the time when we are taking the samples, they are parallel to each other. So angle between them will be 0, cos 0 will be 1. Okay. Now we start the derivation part diagram. That's enough, more than enough. We can make it beautiful later. Okay. Now let me write something related to or to start the derivation. A small derivation it is. Okay. Manageable, no tension actually. The electric field intensity at any point P on the surface of the sphere electric field intensity we studied before, that I am writing. The electric field intensity at any point P on the surface of the sphere. If you want, you can make beautiful sentence like of the surface of the sphere of radius r is. Okay, that is up to you. So E is equal to electric field equation is writing. When you write the electric field equation, you can write 1 by 4 pi epsilon 0 or K you can write. K Q by R square unit vector R cap. Okay. So E is equal to K into Q by R square R cap. Electric field expression is ready now. What is next? We are going to write a little bit more because later we want to use this value. And also whenever you do the derivation, present it maximum simplified way, understandable way. That will give a good impression on your presentation. So everybody know that here small letter r is the unit vector, right? That is r cap is the unit vector, but still write it. So where r unit vector r it is, okay? R is the unit vector directed from, you know, the direction which is visible in the diagram, okay? Directed from O to P, okay? And sometime we will not get enough time in some derivation. That time you adjust the time. Otherwise, present maximum simplified way and show all the steps. Okay. So as this is a mathematical term, the work is going slowly. Please adjust with me. And some people like that also, like slowly going, so they will easily catch everything. Now this is the time to write the flux. So the flux over the area element is, we are going to write the flux equation, okay? Remember, this is to prove Gauss's theorem. Directly don't put Gauss's theorem here. Answer will be the Gauss's theorem, okay? So flux over the area element is d phi is equal to E dot ds, and substitute the value of E now in that E place. So K Q by R square, R cap we can write last, okay, into ds is actually ds cos theta. When you write in scalar form, that is ds cos theta. Can you see that I am giving a tick mark, theta is equal to 0 here. Why? Because the ds and the electric field are in the same direction, angle between them 0. Yeah, so cos 0 is angle between, you know, that was the two variables E and ds, okay? So definitely that is 0 in this case. If that is 0 in this case, cos 0 value is, what is cos 0 value? What? 1 or 0? 1. Okay, cos 0 value is 1, sin 0 value is 0, okay? So d phi is equal to, we write the value, k is there, then q is there, by r square is there, then ds. Not writing cos theta because its value is 1, right? Into 1, if you want you can present, but not required actually. So total electric field, you know, the total calculation from the d phi, ds, dx, right? What is that method? There are two methods. Method number 1 is apply summation symbol. Method number 2 is apply integration symbol. Both are okay for this task. Finally, we are going to find what is the total surface area of the sphere. Final target is that one. So which method you prefer, you can go with that one. So total electric flux over the entire surface of the sphere is phi is equal to, I like to go here with the integration symbol. It can be summation also if you learned, you continue with that. Closed integrals E dot ds is equal to, the time to substitute, k q divided by r square, okay? Why I wrote this one? Because these three things are constant in the integration, okay? So I wrote outside k q by r square and only put integration inside ds. How to identify the variable and constant I explained in previous video. The variables coming after d along with the d, small letter d is considered as variables. Everything else you can write outside this one, constant. So here constant k is a constant, 9 into 10 raised to 9 is 1 by 4 pi epsilon 0, that is 9 into 10 raised to 9 is the value. Kq by r square integral ds. Integral ds meaning is the total surface area of the sphere. That is the meaning of integral ds. ds is a small portion of area of the spherical body, okay. So total surface area of the sphere is 4 pi r square. So here integral ds is 4 pi r square. We can put this in the above equation. So phi is equal to, I gave a tick mark there for which equation, k q by r square. Time to substitute now. What is integral ds is 4 pi r square. Yeah, 4 pi r square. If anything there cancellation possible, you can. So here first we want to keep the value of k, then you can cancel. Value of k we know that 1 by 4 pi epsilon 0. So here phi is equal to 1 by 4 pi epsilon 0 q by r square, then 4 pi r square. Okay. The time to cancel now. You can see there are few variables we can cancel. First variable is 4 pi and 4 pi, both are there in numerator, denominator, r square and r square. What left now? Phi is equal to numerator only one variable left, denominator also one variable. The denominator 1 by epsilon 0 and q. This is actually the Gauss theorem, right? We did it. Actually we achieved it. We proved that phi is equal to 1 by epsilon 0 times q. This is Gauss theorem. This is the proof of Gauss theorem. Okay, so statement is total electric flux over a closed surface is equal to 1 by epsilon 0 times the net charge enclosed. Exactly that came now. Phi is equal to 1 by epsilon 0 times q. I am just rewriting here, nothing new. Phi is equal to integral E dot ds is equal to 1 by epsilon 0 times q. That's all. Okay. One of the good topic, right? An important topic. This is the last topic of the lesson, but doesn't mean that the last part of the lesson, last topic I am saying, like Gauss theorem and proof. There are three more things, that is the application of Gauss theorem, that actually coming in the upcoming videos. There are three more videos from this lesson for each application. Okay. So look into this one. Overall, how is the explanation? Did well? What do you think? Better than what you studied before? Then definitely I expect a subscription from you. Okay, subscribe to the channel if you are not done yet, and kindly share with your friends, the classmates. Let them learn from these videos. Okay students, overall okay, right? If you want, you can make beautifully this diagram. You can see there is a small addition you can do if you want. It's not mandatory, but you can do it. Okay, I'm just scrolling till down to show you how it is. Is it the time to, okay, time to close now? Yes, this is the time to end the video. Okay students, thank you. Have a nice day. We will see in next video, application of Gauss theorem. Thank you. Bye.